the coordinate plane, graphs of equations, circles. Let's recall that the coordinate plane is basically just two real number lines that we typically call the x-axis and the y-axis. And then that divides up the plane into four quadrants. We have the first quadrant here, second quadrant, third quadrant, and fourth quadrant. And we can use this coordinate plane to locate points. So notice that the point corresponding to x equals a on the x-axis and y equals b on the y-axis has the coordinates a and b. So here we have several examples of points in the coordinate plane. Take a moment to make sure that you understand each of these points and their coordinates. We can graph regions in the coordinate plane. For example, suppose we are talking about the set of all points x and y such that x is greater than or equal to 0. In the coordinate plane, that would correspond to all of the points that you see here. All of these points have a positive x value, right? We don't want to include points over here because on this side, the x value is negative. Now it is x is greater than or equal to 0, and so we are also including this vertical line here. Now there are, of course, y coordinates to all of these points as well, but this makes no mention of what y needs to be, and so in this case, y can be anything, which is why we're including positive values of y, negative values of y, and also where y is equal to 0. In the second region, we want to graph all of the points xy such that y is equal to 1. So if we locate y equals 1 on the y-axis, all of these points on this horizontal line have a y coordinate equal to 1. Now, like the previous example, this equation makes no mention of the x coordinate. So x can be anything. So that's why we have this horizontal line. Notice that over here, x is positive. Over here, x is negative. But again, the main thing is y has to be 1. And finally, the set of all points x, y such that the absolute value of y is less than 1. So recall that absolute value means distance from 0. So if the absolute value of y is less than 1, this would mean that y would have to be in between 1 and negative 1, right? Because the distance that y is from 0 has to be less than 1 unit. So what does this look like in the coordinate plane? Once again, x can be anything, so we're not concerned about what x is. But here's y equals 1. Here's y equals negative 1. And if y is going to be in between 1 and negative 1, it would be all of the points in between these two horizontal lines. Now, an important detail here, notice that the lines themselves are dotted lines or dashed lines. And this is because it's strictly less than. There is no equal to here. So if this had an equal sign below the less than sign, we would have solid lines here, like we had over here. Next, let's talk about the distance formula. The distance between 2 points A and B is given by the following formula. This is assuming that A has x and y coordinates x1 and y1, and B has x and y coordinates x2 and y2. Now, the distance is this formula. I won't derive it here, but it basically just comes from the Pythagorean theorem. So let's do an example. Which of the points P or Q is closer to the point A? Well, to do this, we have to find the distance between P and A, and then the distance between Q and A. So let's go ahead and do that. So first of all, the distance between P and A, according to the formula, is the square root of, now we're going to subtract the x coordinates. So here's the x coordinate of P, here is the x coordinate of A. It doesn't matter the order in which you subtract these. but you should get in the habit of subtracting your x-coordinates and your y-coordinates in the same order. So I'm just going to take 1 minus 5, and then we're going to square that, plus, and then for the second part, we are subtracting the y-coordinates. Here's the y-coordinate of P, here's the y-coordinate of A, and again, I'm just going to subtract those in the same order. So if I do the math here, I have the square root of -4 squared plus -5 squared, and this is the square root of 16 plus 25, which simplifies to the square root of 41. And now we're just going to do the same thing for the distance between the point Q and A. So now we are focusing on this point and this point. So once again, we'll go ahead and subtract the x-coordinates. So 8 minus 5, quantity squared, plus subtract the y-coordinates, 9 minus 3, quantity squared. Let's simplify. We have 3 squared plus 6 squared. This is the square root of 9 plus 36, which is the square root of 45. Now, I can simplify the square root of 45, but in this case, it's easier if we don't. You should know that the square root of 45 is bigger than the square root of 41, right? So which distance is smaller? This distance. So what does that mean? It means that P is closer to A. The midpoint formula gives you a formula for finding the midpoint of the line segment that joins two other points. So for example, if I have a point A, which is right here, and a point B, which is right there, if I draw a line segment connecting A and B, the midpoint would be the point on the line segment exactly halfway in between A and B. And that is given by the formula that you see here. Now, what is this formula really saying? It's saying that the x-coordinate of the midpoint is simply the average of the x values of your endpoints. And the y-coordinate of your midpoint is the average of the y values of your endpoints. So, as an example here, show that the quadrilateral with vertices P, Q, R, and S is a parallelogram. And the way we can do that is by proving that its two diagonals bisect each other. Let me go ahead and draw a diagram of what we're looking at here. So here is a sketch of those 4 points. And you can tell it kind of looks like a parallelogram, but to prove it, what we're going to do is find the midpoint of S and Q, and then we'll find the midpoint of P and R, and we're going to show that those are the same point. So let's go ahead and take a look at the segment SQ. To find the midpoint there, we are going to look at the point S and the point Q, and we're going to take the average of the x values, so 2 plus 4 divided by 2. And then same thing for the y coordinates, we're going to take the average there, so 7 plus 4 divided by 2. And this gives us the point 6 divided by 2, which is 3, and 11 divided by 2, which is 11 divided by 2. So that is the midpoint of SQ. Now let's take a look at PR, and we'll do the same thing here. We'll just take the midpoint of P and R. So if you look at point P and point R, the midpoint there is going to be 1 plus 5 divided by 2, and then 2 plus 9 divided by 2. And this is the same thing, 3 11/2. So since the midpoint is the same for both of these, and since the midpoint means it's exactly halfway in between, that means that each one of these diagonals is bisected by this point. And anytime two diagonals of a quadrilateral bisect each other, the quadrilateral must be a parallelogram. What is the graph of an equation? The graph of an equation in x and y is the set of all points xy in the coordinate plane that satisfy the equation. So as an example, let's sketch the graph of the equation 2x minus y equals 3. Now the first thing to note here is that if I have 2x minus y is equal to 3, usually when we graph something, it's a little bit easier if we solve for one of the two variables. And typically the variable we like to solve for is the y variable. Now notice that in this equation, this y is negative, so I can add y to both sides. That's going to get the y on the right-hand side, but it's also going to make the y positive. And then to solve for y, I just need to subtract 3 from both sides. And this gives us 2x minus 3 is equal to y, or to write that in a little bit better way, we're going to say y equals 2x minus 3. Now to sketch the graph, we're just going to plot some points. Okay, so what that means is I'm just going to let x be equal to some numbers, and I'm going to find the corresponding y values. And in this case, this is actually just going to be a line. So we only really need 2 points, but I'll get 3 or 4 points. So for example, what do we get if x is equal to 0? So if we plug in 0 here, we're going to get y equals 0 minus 3, which is negative 3. Let's let x equal 1. If x equals 1, y is going to be 2 times 1 minus 3. This is 2 minus 3, which is negative 1. Let's plug in a negative value for x. So if x is negative 2, y will be 2 times negative 2 minus 3, and this works out to be negative 7. And we'll do one more here. If y equals positive 3, if x equals positive 3, y is going to be 2 times 3 minus 3, which is 6 minus 3, which is also 3. So we have those 4 points. Now all we need to do is plot those points. And so if we plot the point 0, negative 3, we get this point here. 1, negative 1 is this point. Negative 2, negative 7 is right there. And finally 3, 3 is this point. And you should notice that all those points line up on a straight line. So this is the graph of all the points that satisfy the equation 2x minus y equals 3. Let's go ahead and do another example. Sketch the graph of the equation y equals x squared minus 2. So once again, we're going to make a table of values here. And I'm going to pick a few values of x. Now, this is not a linear equation, so we are not going to get a line. And you know that because you have x squared. So what I'm going to do is plug in x equals 0, x equals 1, x equals 2, and then x equals negative 1 and negative 2. And then we're just going to plug those in. So for example, when x equals 2, y is going to be 2 squared minus 2, which is 4 minus 2, which is 2. If x is equal to 1, y is going to be 1 squared minus 2. And when you do the math on that, you get negative 1. If x is 0, y will be 0 squared minus 2, which is negative 2. And now when you plug in negative 1, don't forget, anytime you plug in a negative, you want to use parentheses. So we have negative 1 quantity squared, which is 1, and then minus 2, which is negative 1. And finally, when x is negative 2, we're going to end up getting 2 again. And now we're just going to bring in a graph and plot those points. And so we have the point 2, 2. We have the point 1, negative 1, 0, negative 2, negative 1, negative 1, and negative 2, positive 2. And if you have some experience graphing these, you'll know that this is sort of a U-shaped or a soft V-shaped graph that we call a parabola. Next, let's sketch the graph of the equation y equals the absolute value of x. This is kind of a special graph. It's one that you should try to memorize. Again, I'm just going to plug in the same values of x that we plugged in last time, but this time it's pretty easy to get the y values. So when x is 2, we're just going to take the absolute value of 2, which is 2. When x is 1, the absolute value of 1 is 1. Absolute value of 0 is 0. Now, when you plug in negative 1, the absolute value of negative 1 is positive 1. and the absolute value of negative 2 is positive 2. And now we just plot these points. So we have the point 2, 2, 1, 1, 0, 0, negative 1, 1, negative 2, 2. And this time you can see that we actually get a V-shaped graph. Now again, the thing to remember is this graph doesn't just consist of these 5 points. It consists of every point that satisfies this equation. Now for the equation y equals 1 divided by 1 plus x squared, we could graph this by hand. You would have to get a number of points because this graph is a little bit more complicated, and we'll learn more about how to graph functions like these in the future. So for this example, let's assume that we just use a graphing calculator to graph the following equation in the viewing rectangle that you see here. Now, what does the viewing rectangle mean? Well, what it means when you say negative 5, comma 5 is it means that the x coordinate is going to be between negative 5 and 5. And then the second one, negative 1, comma 2, means that the y coordinate will be between negative 1 and 2. Now, when you graph this on a graphing calculator or any other graphing software, you will notice that you get this shape of a graph here. And again, you can see that x goes between negative 5 and 5, and y goes in between negative 1 and positive 2. But this is a very different graph from the previous examples. Let's define intercepts. So the x-intercept is simply the x-coordinate of the point where the graph crosses the x-axis. How do you find them? You let y equal 0 and then you solve for x. So over here in the graph, for example, this graph would have 3 x-intercepts. Y-intercepts is the same concept. It's just the points on the y-axis where the graph crosses. And to find them, you set x equals 0 and then you solve for y. And so you can see here this graph, for example, has 2 y-intercepts. So as an example, let's find the x and y-intercepts of the graph of this equation. Now you might remember we graphed this equation here just a few minutes ago, but this will give us kind of an alternative way to graph it. So to get the x-intercepts, what we do is we let y be equal to 0. So I'm going to plug 0 in here. That gives us 0 equals x squared minus 2. And now we need to solve for x. Now we'll talk a little more about solving this stuff in the future. Or actually, you should kind of know how to solve it now, but the easiest way to do this is just adding 2 to both sides. We get 2 is equal to x squared. And then if we take the square root of both sides, we end up getting the square root of 2 is equal to the square root of x squared is technically the absolute value of x. And then that means that x itself can either be positive square root of 2 or negative square root of 2. To get the y-intercept, we simply let x equal 0. This is a little bit easier. We're just going to plug 0 in here, and that's going to give us y equals 0 squared minus 2, which is y equals negative 2. Now, using this, we can sketch a graph. And the way we're going to do this is we're going to graph the y-intercept, which is negative 2. That's this point right here. That's where it crosses the y-axis. Then we're going to graph the x-intercepts. Now, the x-intercepts are positive and negative square root of 2. We need to know the square root of 2 is approximately equal to 1.4. So we're going to have one x-intercept at positive 1.4 and the other one at negative 1.4. And if you know that this is a parabola, you can sketch a graph of this equation, a very rough sketch of a graph by just using the intercepts. Next, let's talk about the equation of a circle with center HK and radius R. So it turns out the equation of a circle is given by this formula, and this just basically comes from the Pythagorean theorem. This is called the standard form of a circle. If the center of the circle is at the point 0, 0, which is actually very common, what that means is that h and k would both be 0. If you plug in 0 here and 0 here, this equation simplifies into x squared plus y squared is equal to r squared. So let's go ahead and graph a couple of circles here. I want to graph the circle x squared plus y squared equals 25. So for this one, the center is just going to be at the point 0, 0. And then the radius of the circle, remember now, this is r squared, right? So if r squared equals 25, then that means that the radius would just be 5. So what does a circle of radius 5 look like when it's centered at the origin? So to graph this, we're just going to go to the center, which is 0, 0. And then if the radius is 5, we're going to go 5 units to the right from the center, 5 units to the left, 5 units down, and 5 units up. And then we're just going to do our best to sketch this circle. And it doesn't have to be perfect, but I think we all know what a circle is supposed to look like. And there is a rough sketch. Now, what about part B? What's different about part B? So you can see it's equal to 25. So once again, the radius is going to be 5. But now the center is a different point. Now, we need to keep in mind that the formula says x minus h and y minus k when the center is hk. So the way to interpret this is whatever you see here, that's the opposite of the coordinate for the center of the circle. So what it means, basically, is for this equation, the center is going to be at the point positive 2, negative 1. And the radius is still going to be 5. So to graph this, I just need to locate a new center. So the new center is going to be at positive 2, negative 1, which is right there. And then we are still going to go 5 units in every direction. So 5 units down would be here. 5 units up would be here. 5 units to the left is here. And 5 units to the right is a little bit off screen. It's right there. And so that circle is going to look like this. So you'll notice that these circles have the same size, but one is centered at the origin and the other one is centered at a different point. Now let's find the equation of a circle. In the first part here, we want to find the equation of the circle with radius 3 and center 2, negative 5. So again, we know the equation is x minus h squared plus y minus k squared is equal to r squared. In this case, h is 2, so that's going to be x minus 2 squared. K is negative 5, so that's going to be y minus negative 5 squared. And then the radius is 3, so 3 squared. Now, we shouldn't leave it like this. We should clean it up. So we have x minus 2 squared plus y plus 5 squared is equal to 9. And this is the equation of the circle for part A. Now for part B, we want to find the equation of a circle that has points P and Q as the endpoints of a diameter. So this is a lot more challenging now, isn't it? Let's try to draw a graph to see just what is going on here. So we have point P, which is the point 1, 8, which is right here. And then the point Q, which is 5, negative 6, which is right there. And those are the endpoints of a diameter. So remember, in a circle, a diameter is any line segment that goes through the center of the circle and touches the other side. Okay? So if I draw this line segment, we know the center of the circle must be the midpoint of this line segment. So we need to find that center by just basically finding the midpoint. So let's go ahead and work on the midpoint of the segment PQ. So to do that, remember we take the x coordinates, so 1 and 5. We're going to add those together and divide by 2. And then we're going to take the y coordinates, so 8 and negative 6, add them together and divide by 2. This is going to give us positive 3 and positive 1, which is right there. Okay, so that's the center of the circle. Now, just to be clear, we don't have to have this graph to do this problem, right? We could have figured this out. But the graph helps you understand what's happening. So the circle goes something like this, okay? So the next thing we need to figure out is what is the radius of the circle? So right now we know the center is 3, 1. So we know that the equation is going to be x minus 3 squared plus y minus 1 squared is equal to the radius squared. And again, we don't know what the radius is yet. There's two ways to find the radius. One way to find the radius would be to just find the distance between the center and one of these 2 points, either P or Q. To do that, you would have to use the distance formula, okay? The other way to do it is to recognize that anytime a point is on the graph of something, the coordinates of that point have to satisfy the equation. So for example, we know that Q has coordinates 5, negative 6. 5 is the x coordinate, negative 6 is the y coordinate. Since it's on the circle, I should be able to plug those into this equation. So if x equals 5, we're going to put that right here. And y equals negative 6, we're going to put that here. And notice that this will allow us to solve for r squared. So this is 2 squared plus negative 7 squared equals r squared. That's 4 plus 49, which is 53, equals r squared. So the radius is actually the square root of 53. But for the equation of the circle, we'll just plug 53 in for r squared. All right, so the equation of the circle is this. Next, we want to identify an equation of a circle. So let's show that this equation represents a circle, and then we're going to find the center and the radius of the circle. And to do this, it will involve the technique of completing the square. So what I'm going to do is rewrite this equation by grouping the x terms together and then grouping the y terms together. And then the number here, I'm going to move that over to the other side. So this equation becomes x squared plus 2x. Now we'll leave a little space, plus y squared minus 6y, leave a little space, and then the plus 7 right here, we're going to subtract 7 from both sides to move it over to the right-hand side. Now we're going to complete the square here. So remember, we need to take half of this number and then square it. So that's going to be 1, and we're going to add that to both sides. And then we're going to complete the square here by taking half of 6, which is 3, and then squaring it, which is 9. And we're going to add 9 to both sides. And now we can factor this. This is going to be x plus 1 quantity squared. Plus, we can factor this, which is y minus 3 quantity squared. And on the other side, we have negative 7 plus 1 plus 9, which is 3. And so the center of this circle is negative 1, positive 3, and the radius of this circle, remember now this is r squared, so the radius is going to be the square root of 3. Next, let's talk about symmetry. When a graph has symmetry, there's basically 3 different types of symmetry that we are interested in. One is symmetry with respect to the x-axis, which means that you have a mirror image of the graph across the x-axis. For this to happen, basically the same x-coordinate needs to produce a positive and a negative y-coordinate. So for example, if y is 3 here, then y would be negative 3 on the other side. To test for this kind of symmetry, you simply replace y with negative y, and if the resulting equation is the same as the original, then you have this kind of symmetry. Y-axis symmetry is very similar. To have symmetry across the y-axis, that means you have a mirror image here. And for that to happen, you have to have the same y value, but opposite x values. So to test for this, we replace x with negative x, and we see if the resulting equation is the same. And if it is, then you have this symmetry. And finally, symmetry with respect to the origin means that you have a mirror image of a point through the origin on the other side. For this to happen, you have to replace x with negative x and y with negative y, and the resulting equation has to be the same. So let's go ahead and take a look at an example. So in this example, let's test the equation x equals y squared for symmetry. First, we'll test for symmetry across the x-axis. So remember, what we have to do here is we have to replace y with negative y, and then take a look at the equation. So x equals y squared is going to become x equals negative y quantity squared. Well, negative y quantity squared is the same as y squared. So notice that the original equation is the same as the equation we get here in the end. So does it have x-axis symmetry? Yes, it does. Now, does it have y-axis symmetry? To have y-axis symmetry, you are going to replace x with negative x, right? So x gets replaced with negative x. So x equals y squared becomes negative x equals y squared. Now, notice that this negative is not going away, right? Because it's not squared like it was up here. So you can't simplify this any further. This equation and this equation are different. So does it have y-axis symmetry? No, it does not. Okay, and lastly, to test for symmetry through the origin, you are going to replace x with negative x, and you're going to replace y with negative y, and then see what you get. So we have the equation x equals y squared. X is going to be replaced with negative x. Y gets replaced with negative y. And now what's the resultant equation? Well, negative x stays negative x. Negative y squared does become positive y squared. But again, the equation you get in the end here is different from the equation that you started with. So no, this does not have symmetry through the origin. So we only have x-axis symmetry, and I won't belabor the point here, but if you go to graph the equation x equals y squared by plugging in some values, you will see that you get a graph that looks like this. And again, now you can see why we have symmetry across the x-axis. And our final example is the same thing. We're going to test this for the different kinds of symmetry. So again, let's go ahead and test for x-axis symmetry. To do this, we're going to replace y with negative y. So if I plug negative y in there, we get this. And no, we do not have x-axis symmetry because this equation is different from the equation that we started with. All right, let's test for y-axis symmetry. To do that, I'm going to replace x with negative x. This is going to give us y equals negative x cubed minus 9 times negative x. This is y equals negative x cubed and then plus 9x. Is that equation the same as the original? No, it's not. So no, we do not have y-axis symmetry. Now for symmetry through the origin, we are going to replace y with negative y, and we're going to replace x with negative x. So y becomes negative y, and both of these x's become negative x. This is going to give us negative y equals negative x cubed plus 9x. But now notice, if we multiply both sides by negative 1, this becomes y equals x cubed minus 9x. And this is the same as the original equation. So yes, we do have symmetry through the origin. Now, what does this graph actually look like? I won't show you all the details here, but it turns out that the graph is going to look something like this. And I want you to notice that if you pick a point over here and you go through the origin, you have a mirror image of that point down there. Same thing here, if I pick a point right here and I go through the origin, there is a mirror image on the other side. That's what it means to have symmetry through the origin. And that concludes this video lesson.